This is a piecewise defined function, and it's piecewise because its graph is in two distinct pieces, right? It's going to have two different formulas, one for each piece. So let's write a formula for this function. Okay. So when we have a piecewise function, you write the formula by putting f of x equals in a big curly bracket, and then we're going to write our two formulas. So what's the formula for that horizontal line? Y equals 2, yeah. So f of x equals 2 is going to be one of my formulas. And then what's the equation of this other line? Very close. The plus 2 is right because that's the y-intercept. What's the slope of this line? -1, because it goes right 1, down 1 to get from one to the next. So this is y equals -x plus 2. So those are my two formulas. And then I have to add my ifs, right? So f of x equals 2 if what? So the y value is 2 if x is where? Less than 0, yep, and bigger than -4 because it doesn't go on forever. So we would say -4 less than or equal to x less than or equal to 0. And then we use the other formula if x is where? Greater than 0 and less than. Okay, so this has to be or equal to because the closed dot on the 4. Now, I can put the or equal to sign either here or here, right? In fact, I can put it both places. It's just bad form, okay? But it's not incorrect. But good form would be to have one of them or equal to, okay? Because they both create a close one. If one's closed and one's open, you're going to have a closed dot here. And if they're both or equal to, you'll still have a closed dot there. It's just you would draw it twice, which is weird. You don't have to draw it twice, right? So if I do it this way, this says from -4 up until 2, but not including the 2, right? Up until 0. And then this one says from 0 to 4, including the 0. So you end up coloring that dot in. And if I switched it, if I had this or equal to and this one not, then this would say -4 to 0, including both endpoints. And then this one would say 0 to 4, not including the 0 and including the 4, and you end up with the exact same picture. So you can put it on both. It's just sort of proper form would be to have it on one and not the other. The reason that we consider this better form is because this is a function, and by having or equal to in both places, it gives the impression, the incorrect impression, that you have two different y values for one x value. Even though the y value is 0 in both formulas, it just gives that like, what? 2 y's for one x? That doesn't seem right. So. All right, so now I want to use interval notation to write the domain of this function, right? The domain is the set of all x values. So what x values does that function live on? -4 to where? 4, including both endpoints. And then the range, that's the y values the function lives on, what is that? -2 to 2. All right, so now we can use this graph to evaluate the function at different x values. So when x is -5, I want to know what the value of y is, what f of x is. So we go to x equals -5. I try to go up to the graph. What happens? It's undefined. There is no graph there. Okay, so if there is no graph there, we just write undefined. And then f of -4, we look at the graph. We find x equals -4. We go up to the graph and read off the y coordinate, which is 2. All right, so I get 2 as my y value for all the x's up to 0. And then when x is 1, go to my graph. When x is 1, find x equals 1, go up to the graph and read off the y value, which is 1. Okay. And then when x is 2, what's the y value of this function? 0. When x is 3, what's the y value? -1 and -2 when x is 4. So we can always refer back to this table if we need to know a value of f. We can also always just look at the graph, right, like we just did. So we can use either one to get y values if we know x values. So we're going to be doing that throughout this lesson. So, all right, so the first thing we're going to talk about is vertical shifts. So the whole idea of transformations is that we're going to have okay, so the topic of transformations is all about creating new functions from a parent. Okay, so we're going to have a parent function. In this case, it's going to be this piecewise function that we just spend a little time analyzing. And we're going to talk about different relatives of this parent. So the first kind of relative is a vertical shift. So I want to create a table where I have x and f of x is already in it. And then I want to create f of x plus 2. Okay, so that's going to be take all of your f of x values and add 2 to them. So if f of x is 2, f of x plus 2 is 4. So these are all going to be 4s. And then 1 plus 2 is 3. 0 plus 2 is 2. 1, 0. So now I'm going to plot my new relative. These are my x's. These are my y's. And I'm going to see what happens to the parent. So I've got -4, 4. -3, 4. Well, those are 4. And then I have 1, 3. 2, 2. 3, 1. 4, 0. So if I connect these, this is my new function, y equals f of x plus 2. And this guy was my parent, y equals f of x. So what happened? How could you describe the transformation that took place between the graph of f and the graph of f of x plus 2? Shifted it up by 2 units. So this is a vertical shift up 2 units. Okay, so when we look at the formula, y equals f of x plus 2, it kind of makes sense that it's going to shift it up 2 units because this f of x just means y, right? Just another way, special fancy name for y. So you're saying take the y coordinates and add 2. Add 2 to every y coordinate. It's going to be a vertical shift by 2 units. So another way to look at this, instead of doing a table, is to look at certain points. So we'll pick a few anchor points from the original graph and look at what happens to them when I add 2 to every y. So my x coordinates are all going to stay the same, and my y coordinates increase by 2. Whoops. 1, 1 goes to 1, 3. 2, 0 goes to 2, 2. So we shift the parent graph up by 2 units, which means add 2 to every y coordinate. So the same shift happens for any value k. You do f of x plus something, okay, then it always is going to shift up. Shift vertically by k units. So if you just tack on a number at the end, it's going to make it move everything up. All right, so here's a little practice. I want you to discuss in your groups. I did a little bit of it for you. We have a parent function, g of x equals x squared. I want you to fill in the table of values for g of x minus 3. Plot it, where this is your x and this is your y. And give a formula for your new transformed function. Okay, so first I'm going to fill in the rest of the values for g of x. So g of x equals x squared, right? That was given up here. So to find values of y, I just square the values of x. So that's how I get the 16. Negative 4 squared is 16. Negative 3 squared is 9. 0, 1, 16. And then I want to do g of x minus 3. So I want to take each of these y coordinates and subtract 3 from them. So 9 minus 3 is 6. 4 minus 3 is 1. 16 minus 3 is 13. So I just took each g of x value and subtracted 3 from it to get the last column. So now I'm going to plot them. I have negative 4, 13, negative 3, 9. Oh, sorry. Negative 3, 6. Negative 3, 6. Negative 2, 1. 0, negative 3. So negative 3 is going to be like right here. Then I have 1, negative 2. Oh, I skipped 1, negative 1, negative 2. Let's look right there. Then I have 1, negative 2. Then 2, 1. 3, 6. And 4, 13. So I connect these. And it looks like I got a vertical shift down by 3 units. So my formula h of x, okay, for my transformed function, that's g of x minus 3. That's my transformation. I took g of x and subtracted 3. But g of x is really has a formula. What is the formula for g of x? X squared. So this is the formula for my transformed function, x squared minus 3. So what happened, to do g of x minus 3, I'm going to shift the parent graph down by 3 units, which means I have to subtract 3 from every y coordinate. So I can do this also by points. Could look at some key points, subtract 3 from every y coordinate. Oops. And then I could plot my key points. Very similar to making the table. Oh yeah, because I gotta subtract 2. You're right. So my general conclusion when you subtract a number is that we have a vertical shift down. Take your original function, shift it down by k units. So vertical shifting is pretty straightforward, right? If you add a number to the very end, it shifts up. Subtract a number from the very end, shifts down. So now we're going to talk about horizontal shifts. Okay. So these vertical shifts, I quickly mentioned before, it makes sense that they're vertical because I'm changing the y coordinates, right? G of x is just a fancy name for y. You're subtracting 3 from every y, of course that's going to move your graph down. It's going to create a vertical change in the graph. So my next relative is when I'm going to add and subtract inside. I'm going to add and subtract to x. So if I'm changing the x value, how do you expect the graph to move? Left and right. Good. So let's see what happens when I do f of the quantity x plus 1. So I'm going to fill in my table of values for f, and it's not fully filled in, which means I can use my graph to get the rest of the values. We had 2, 2, 2, it's already there. And then 1, go to my graph, find the x value of 1, the y value is 1. And at 3, the y value is -1. That is such a good question. F is undefined at -5. This is a different function, a relative of f, in which I can put in a -5 because I'm going to add 1 to it before I apply the rule f. So if I have -5 and I add 1, now this is f of -4, which does exist. So yeah, why can I plug in a -5? Well, oh, sorry, I should say this one's undefined. Yeah, okay, good. When x is -5, f is undefined, right? But this relative of f is not undefined because I can take that -5, replace my x with it. I'm going to do f of -5 plus 1, and the order of operations says do that addition that's in parentheses first. So we take the -5 and add the 1, and we get -4. Then we can apply the rule f because that number, -4, is in the domain. Right. You could not do -6 because -6 plus 1 would be f of -5, not in the domain. Yes. Uh-huh. Yeah. F of -3, I can look up in this table of values, or I can look up in my graph. This is the graph y equals f of x. So f of -3, I find x equals -3, go up to my graph, it's 2. Okay, so you're going to take each x value, add 1 to it, then apply the rule f. So this is going to be f of -3 plus 1, which is f of -2. And f of -2, I can look up in my table and get 2, or I can look up in my graph and get 2. Now I have f of -2 plus 1, right, because I'm plugging in this value for x. And I end up evaluating f of -1, which is 2. And then I have f of -1 plus 1, which is f of 0. And f of 0 is 2. And now I'm going to do f of 0 plus 1, which is f of 1. And what's f of 1? 1. And then f of 1 plus 1, that's f of 2, and f of 2 is 0. All right, what am I taking f of in this case? 2 plus 1. Great. I'm plugging in these x values. So I'm replacing this x right here with these values here. So my value for x is 2. So I'm going to do f of 2 plus 1, which is f of 3, which is negative 1. And then f of 3, I get when x is 3, I'm going to do f of 3 plus 1, which is f of 4, which is negative 2. And when x is 4, I get f of 4 plus 1, which is f of 5, which is what? Undefined. So my old function f, its domain went from negative 4 to 4, right? Negative 4 to 4, that's where it lives. My new function, my relative, its domain goes from negative 5 to 3, right? The undefined, it doesn't get undefined until negative 6, like you pointed out to the left. And at the right, I can no longer plug in 4. 4 could go into f, but it can't go into this relative f of x plus 1. So my domain shifted to the left. Right? Now it goes from negative 5 to 3. I can plug in one smaller value than I could before. And I can only go up to 3 instead of 4 because I have to add 1 to the input before I can apply the rule. So if I plot these values, I get negative 5, 2, negative 4, 2, 1, 2, and then 0, 1, 1, 0, 2, negative 1, 3, negative 2, and 4, undefined. So this is my new graph. So we were correct in our guess that we were going to move the graph left and right because we were changing the x value. But is this what you would have predicted to happen? What would you have predicted? Right one, yeah, because that positive sign makes you think right, positive to the right, negative to the left, positive up, negative down. So with vertical shifting, it works exactly like you expect. If it's plus, it goes up. If it's negative, it goes down. But with horizontal shifting, the opposite of what your intuition tells you ends up happening. And we can, now that we've dug in a little bit, we can see why, right? Because if you're going to add 1 to your input, that means that you can make your x value 1 smaller than you could before and still have the function be defined. So if you can make x smaller, you're moving the graph to the left. So to describe what happened to the original graph of f to get this new relative, we shifted left 1 unit. So if I wanted to do this by points, I would look at my relative, the f of x plus 1, the transformation, and I would say, okay, I know that that means that I'm going to shift my parent graph left, right? The plus sign indicates left by 1 unit. And to shift 1 unit to the left, that means I need to subtract 1 from every x coordinate. So my y coordinates all the same, all stay the same. You take your x coordinates and subtract 1. So I get negative 5, negative 4, negative 3, negative 2, negative 1. Oops. Zero. Negative 4. Oh, I see. I left one out. So this is negative 5, 2. Negative 4. Negative 3, negative 2, negative 1, 0, 1, 2, 3, and then this is now on. that's the last place that f is defined. So. Oh, something doesn't match up. So 3, looks like I left out. So the y coordinates are not supposed to change. So 1, 1. So that's perfect. So the 1, 1, this point here, the y coordinate's not supposed to change. Just the x coordinate goes left 1. So this should become 0, 1. So I messed that up. And then 2, 0 should become 1, 0. Y coordinate stays the same. And then 3, negative 1 becomes 2, negative 1. And 4, negative 2 becomes 3, negative 2. There you go. So if k is positive and you add it to the input of your function, to the x part, that's going to cause a shift left. This is a horizontal shift left k units. So if you add to the input, it moves your whole graph left. All right, so now I'm going to have you try one. We have an x cubed. I gave you part of the table. I want you to fill it in, sketch the graph, and give me a new formula for the relative h of x minus 2. Okay, so filling in my table, the h of x parts aren't all filled in, and h of x is the rule that cubes things, right? So that was given in the question here. So h of x takes whatever input you have and cubes it. So negative 2 cubed is negative 8, 0 cubed is 0, 2 cubed is 8, 4 cubed is 64. Okay, so that gives me x comma h of x. All those points are plotted in the graph that's already done for you. We're interested in what h of the quantity x minus 2 looks like. Okay, so I want to plug in my x value first, right? Take the x value, negative 4, plug it in here for x. Then you do what's in parentheses first, right? So this becomes h of negative 6, which is negative 216. And when x is negative 3, I'm going to end up taking h of negative 5. Negative 3 minus 2 is negative 5. Cube negative 5, and you get negative 125. And then this becomes h of negative 4. When you cube negative 4, I happen to know because I can look up in this table, x is negative 4, h of x, which is negative 4 cubed, is negative 64. And then here I'm going to get h of negative 3, which is negative 27, h of negative 2, which is negative 8, h of negative 1, which is negative 1, h of 0 is 0, h of 1 is 1, h of 2 is 8, and h of 3 is 27. So then I'm going to plot x, comma, y. Okay, so a lot of these I can't even fit on here. So let's do negative 1, negative 1. Sorry. The first y value that will fit on my graph is negative 1, so that's 1, negative 1. 2, 0 is on my graph. And then I have 3, 1. and 4, 8, which is way off the graph, way up here. But I can already see the shape, right? This area in the center shifted to the right. So I've got something like this. So my new function, k of x, right? This is going to be k. We're just giving it a new name, plucked out of thin air, k, right? You can also just call it y equals. This relative was h of x minus 2. But h is the function that cubes things, right? So this ends up being x minus 2 cubed. So if we start from a perspective of knowing what this transformation is going to do, right? If I say, oh, h of x minus 2, oh, that's definitely going to be a horizontal shift right by 2 units. That means I have to add 2 to every x coordinate. So this table looks like it's right. So I end up with -2. Oh, add 2, sorry. -1 plus 2 is 1. So you can just pick a few key points. We know that it's going to shift right 2 units, so to shift right 2 units, add 2 to every x coordinate. All right, so we can do 2 shifts in one relative. Okay, so this is a multiple transformation. My relative has 2 different shifts in it. What is the parent function in this graph? I mean, in this formula. What is the function that's being shifted around? Yes. Y equals x squared. And then what's my vertical shift? Down 3 units. Yep, the stuff that's tagged on at the end, that's my vertical. So I'm going to shift down because it's negative 3 units. Okay. What's my horizontal shift? Left 2 units. Yeah, the stuff that's inside that's changing the x is this plus 2. That's how I'm changing x. Because it's positive, I know I'm going to shift left 2 units. So all the points on the graph, an original xy is going to go down 3, which means I have to subtract 3 from my y coordinate, and left 2, which means subtract 2 from my x coordinate. So any point on the graph is going to go left 2, down 3, which means subtract 2 from x, subtract 3 from y. So now I'm going to draw the parent function, x squared. We should be pretty familiar with what it looks like. 1, 1, 2, 4, -2, 4, 3, 9. So this is y equals x squared. I just picked a few random x values and squared them, plotted the points. Now I have to take this graph and shift it left 2, down 3. So I can just pick the few key points I already plotted and move them left 2, down 3. 1, 2, down 3. And then this one would go left 2, down 3. This one at -2, 4 would go left 2, down 3, lands there. And then I have negative 3, 9 to go left 2, down 3, lands me there. And then I can do the same thing for the other key points over here. This one at 1, 1, I go left 2, and then down 3. And left 2, down 3. Left 2, down 3. And I've got all my key points plotted. And this is the graph y equals x minus 2 squared minus 3. All right, so I want you to turn to page 10. And, oh, did I skip? I skipped something. Okay, do A through D. Turn to page 10 and do A through D. All right, so let's look at A. I have my original function right here. It's just a piecewise function, so there's no, it does have a formula, but it's a complicated, it's got 3 different pieces. So rather than thinking about the formula, we're just going to shift it around by adding to the y or adding to the x. Adding and subtracting to y, adding, subtracting to x. So A says y equals f of x plus 2. So I'm tacking a plus 2 onto the y coordinate, which means what's this transformation going to look like? Vertical shift up 2 units. So I want to look for a graph that looks just like this one, just like the parent, but everything is shifted up 2 units. So which of these looks like that? Yep, the first one in the second row. Looks exactly like the parent. I just moved the whole thing up 2 units. Yep. All right, so for B, this is f of the quantity, x plus 2. So this time I'm adding 2 to my input instead of adding 2 to my output. So if I add 2 to my input, what kind of transformation does that cause? Horizontal shift to the left 2 units. So I'm looking for a graph that looks like this one, but shifted left 2 units. And if it helps, you can just draw it, right? Pick a few key points, move them left 2. Sketch it. There's my graph moved left 2 units. Which of my graphs looks like that? The second one, yes. It looks just like this one because I just ran out of room, right? So this one's B. Because I used the same window for all of them. Some of them just left the window. And for C, I have y equals f of x, f of the quantity, x minus 2. So this time I'm subtracting 2 from x. So what kind of transformation will that cause? Horizontal to the right 2 units. So pick a few key points here, move them all to the right 2. And my graph will look like this. So which of my graphs looks like that? The last one. Yep. Again, I just lost the very end of it because I used the same window for all my graphs. All right, and for D, D is f of x minus 2 plus 2. So I've got two transformations. What does this minus 2 in parentheses tell me to do? Yep, right 2, and the plus 2 outside says up 2. So I'm going to move all my key points right 2 and up 2. Right 2, up 2. This point goes 1, 2, 1, 2. This x-intercept goes right to up 2. Y-intercept goes right to up 2. Right to up 2. Point goes right to up 2. So this is my new graph. Which of my graphs looks like that? This third one right here. Very good. So how do you guys feel about transformations so far? Good? Shifting left and right, up and down. Okay, so what I want you to do now is in this last 10 minutes that we have, and finish before next class, if you don't finish in 10 minutes, I want you to study what happens when this time we're still going to make changes to the y and to the x, but instead of changing by adding or subtracting something, we're going to change by making them negatives. Okay, so first we're going to experiment with just taking the y coordinate and making it negative. And then I'm going to have you experiment by taking your x coordinates and making them negative. So it's important to remember that this negative sign can be read as the opposite of. Right? So if something's already negative, throwing a negative in front will make it positive. All right, so I'll come around and help. I want you to try to work through what happens on your own.